Hello, welcome to this presentation. My name is Frank Lemoine from the NASA Goddard Space Flight Center. I am a member of the International DORIS service. Our objective today is to give you an overview of DORIS as a space geodetic technique, the products that are produced using DORIS data, and how the technique contributes to the International Terrestrial Reference Frame. I'd like to acknowledge here my co-authors from the Central Bureau of the IDS who have contributed to this presentation. DORIS is an acronym which means Doppler orbitography and radio positioning integrated by satellite. It is a civil satellite tracking system designed by the CNES, the French Space Agency, and the IGN, France's mapping and survey agency, in the 1980s for precise orbit determination and accurate ground positioning. Over the years, DORIS has become one of the four space geodetic techniques, along with GNSS, SLR, and VLBI, that are used to define the International Terrestrial Reference Frame. DORIS was developed to support the French-US TOPEX Poseidon mission, which was dedicated to the precise measurement of the ocean surface topography using a radar altimeter. The DORIS technique is based upon the accurate measurement of the Doppler shift of radio frequency signals transmitted from ground beacons and received on board the spacecraft, as shown in the image on the right. Every 10 seconds, the DORIS receiver measures the Doppler shift in the frequency of the radio signals transmitted by the ground beacons. The current DORIS receiver can track the signals of up to 7 beacons when they are visible to the satellite. The Doppler measurements are made at two frequencies, 2.036 gigahertz at S-band for precise measurements, and at 401 megahertz to allow for the ionospheric correction of the propagation delay. The overall DORIS system includes a global network of transmitting stations, onboard receivers in a satellite constellation, and a control center in Toulouse, France, to receive the DORIS satellite data. The DORIS signal is free, and there are no restrictions on its use. There is also no limitation on the number of satellites that can carry DORIS receivers. The DORIS instrument includes an omnidirectional dual-frequency antenna, a receiver with two receiving trains, primary and backup, that measure the radial velocity, and an ultra-stable oscillator, USO, for both the primary and the backup receiving chains. The onboard software includes a navigator software called Diode, which allows for onboard real-time orbit determination using a Kalman filter. The system availability is excellent, close to 99%. The orbit determination quality of the real-time orbits is at the level of a few centimeters. The accuracy of the radial velocity measurement is about 0.3 millimeters per second. The radial orbit accuracy of the DORIS orbits used for scientific studies is less than 10 millimeters radial RMS. A new generation of DORIS receiver, the fifth in the flight series, is under development by the CNES. On this slide, we provide a complete overview of the DORIS constellation for the past, present, and the future. The current DORIS constellation includes 9 operational satellites. This configuration provides users or scientists with access to more DORIS data than ever before. DORIS satellites include missions from a broad mix of space agencies. ESA, the European Space Agency, with Cryosat-2, Sentinel-3, and Sentinel-6, NASA, with Jason-3 and the SWAT satellite, ISRO, the India Space Agency, with Soral, and CNSA, the China Space Agency, with the HY-2 series of satellites. The breadth of missions demonstrate the international commitment to the DORIS system and the critical role it plays in Earth observation, oceanography, and geodesy. DORIS has a global network of about 60 stations, built up through close cooperation with partners in 35 countries. In order to meet the needs of precise orbit determination, the station geographic distribution was designed to be as homogeneous as possible, with half of the stations located on islands or in coastal areas. Co-location with other space geodetic techniques, GNSS, SLR, and VLBI, is another feature of the DORIS network. As half of the current stations were commissioned before 1995, we have long time series of positions, which is also of great interest for geodesy. On the right-hand side, we show a few photos of DORIS stations, including 2 in Latin America, Arequipa in Peru, and Socorro Island in Mexico. DORIS stations are made up of the following components. What we call the beacon is the transmission and control unit that generates the dual frequency DORIS signal. The outdoor equipment includes the antenna and 2 external boxes. First, the amplifier that restores the nominal power to the signal after passage through the cables, and second, the smaller box that contains the remote control system, the GPS sensor, and the meteorological sensors. The antenna transmits the signal generated by the beacon and contains the reference point to which the coordinates are assigned. DORIS stations operate continuously, and the antenna must have good visibility for low Earth orbiting satellites, with a clear sky visibility to 10 degrees elevation. The DORIS stations need to be installed on very stable monuments in order to accurately monitor crustal deformations. The International DORIS Service was founded as a service of the International Association of Geodesy in 2003. The objectives of the service are to provide access to DORIS data and products, to provide documents that support the data analysis, and to develop and to support scientific applications with DORIS data. The IDS contributes to the IERS realizations of the International Terrestrial Reference Frame and supports the objectives of GGOS. The IDS consists of a central bureau to coordinate activities, a governing board to provide overall direction, analysis centers that contribute DORIS products, a combination center that combines DORIS products and coordinates submissions to the ITRF, and data centers that serve as DORIS data and product repositories. The IDS has also established special working groups to focus on special topics, such as near real-time applications for the ionosphere and for correction of DORIS data using external clocks. Let us now look at a few scientific applications of DORIS data. First, we will look at some results using DORIS data from Socorro Island. Since 1991, Socorro Island, part of Mexico, has hosted a DORIS beacon. If we look at the time series of north, east, and up coordinates of the early Socorro station, the blue dots, we see a nonlinear behavior which is often explained by post-seismic deformation. The IDS has completed a scientific study which allowed us to identify a submarine volcanic eruption in late January 1993, 4 kilometers away from the island, as the cause of the deformation. Moreover, the station data allowed us to develop an exponential model for the motion of the Socorro station up to mid-1998. DORIS may also be used to monitor the impact of ice melting on the vertical land motion. Looking at the time series of the up component of the DORIS station in Thule in northwest Greenland, the red dots on the plot, we see an acceleration of the uplift starting in 2006. The same behavior is observed from data provided by co-located GNSS receivers, here shown in blue. An IDS study confirmed a similar pattern in the equivalent water heights derived from data from the GRACE mission, and correlated that pattern with an acceleration of the mass loss by the surrounding glaciers near Thule. Since 2008 and the creation of the IDS Combination Center, the IDS has contributed to the realization of the International Terrestrial Reference Frame by delivering combined solutions from multi-satellite DORIS Analysis Center series. For ITRF 2020, the IDS delivered 1,456 weekly solution files from 1993 to 2021, including weekly station coordinates and daily Earth orientation parameters. On this series of plots, we depict the time series of the scale and the translations of the IDS solution with respect to ITRF 2020. With the vertical gray lines, we indicate the time evolution of the DORIS constellation in regards to the number of beacons that can be simultaneously tracked by the particular generation of the DORIS onboard receiver. From the plots, we observe that since mid-2002, the scale, X, and Y translations almost lie in a band with a range of 10 millimeters. Mid-2002 was when the second generation of DORIS receivers, tracking 2 beacons at one time, started to be included in the DORIS satellite constellation. The Z translation shows larger values as it is highly sensitive to the modeling of solar radiation pressure and atmospheric drag on the DORIS spacecraft. This modeling is very challenging due to the low orbital altitudes and the complicated shape of the DORIS satellites. If we now look at the station position residuals, we clearly see that the results are improved when more satellites become available, and with the most recent generation of DORIS receivers. The 3D weighted RMS of the DORIS station position residuals are better than 7.5 millimeters since mid-2008. This was when the JSON-2 DORIS receiver started to routinely deliver DORIS data from the third generation of DORIS receivers that had the ability to track up to 7 DORIS beacons at one time. The IDS also delivers daily estimates of the Earth orientation parameters. The comparison of the DORIS X and Y pole coordinates with respect to the IERS C04 series, as depicted by these plots, show that the results are improved when more satellites become available and with the most recent generation of DORIS receivers. Since 2015, the DORIS constellation has only included DORIS receivers of the third generation. The standard deviation of the differences of our pole estimates with the IERS C04 series have been on the order of 200 microarcseconds, which is about 3 times smaller than in the 1990s. To support precise orbit determination for altimetry missions, the International DORIS Service regularly estimates the extension of the DORIS terrestrial reference frame for precise orbit determination. The solution includes mean positions and velocities of all the DORIS stations since 1993. This solution is aligned onto the current realization of the ITRF, and so can be seen as a DORIS extension of the ITRF. The DPOD solutions are obtained from the stacking of the latest IDS combined solutions and are computed operationally twice a year to include the latest DORIS stations and to take into account the latest geophysical events which might affect the position and velocities of the DORIS sites. We would like to point out different ways for you to join the IDS community. A vast amount of material is available on the IDS website. We have regular meetings through the IDS Analysis Working Group and IDS workshops, and meetings of special working groups. If you are interested in these activities, you should contact the IDS Analysis Coordinator or the IDS Working Group co-chairs. We provide regular newsletters and annual activity reports of IDS components, which are all available on the IDS website. We offer introductory courses and seminars entitled DORIS Days. Please contact the IDS Central Bureau for more information. In closing, let us summarize a few key points. DORIS is one of the 4 techniques of space geodesy. DORIS is based on the dual frequency transmission of signals from ground beacons to satellite receivers. DORIS missions are assured at least through 2035 and beyond. This includes the DORIS participation in the ESA Genesis mission dedicated to the ITRF. The DORIS network includes about 60 ground stations, more or less evenly distributed around the globe. A densification effort is underway and new stations are planned. DORIS scientific applications are promoted by the International DORIS Service, which has been a service of the International Association of Geodesy since 2003. Thank you for your interest in the DORIS system and in the International DORIS Service.